Welcome. We're going to be talking about numbers today. It's all about numbers and using the clues to find unknown numbers, unknown digits. So I'm Tony Bearden. I started AIMSEC about 20 years ago, and before that NRICH. And I'm still very much involved with creating and exploring new resources for teaching. Marilyn?
Right. Hello, I'm Marilyn Buchanan. I'm a retired professor from California State University. My interest is in teaching mathematics and learning mathematics in the primary school. And I work for Tony at NRICH and have maintained contact since then. Hello.
Yes, it was a while back, wasn't it?
It was 20 years ago.
More than that, actually.
Oh,
No.
right, it was. Yeah, 24. Yeah.
So, unfortunately, Caroline is not well, so she's here behind the scenes, and she'll be helping us a little the techie aspects of this. But it'll be Marilyn and myself who are conducting the workshop. So, without ado, let me tell you about the program. So, we're going to be working on knowledge and skills and how to develop the children's understanding of place value, of methods of calculation, of mathematical thinking, how to make our learners into real mathematicians, and systematic planning and working to find all solutions. If there isn't just one, finding them all, and visualization. And we usually plan our workshop on a spiral. So we start with very young children. And as you imagine that spiral of the school is the school years, and it goes around and around, and we keep revisiting the same topic. But of course, each time the children meet the same topic, they add to their knowledge, extend their knowledge, and deepen their knowledge. And of course, if they haven't got this secure foundation in primary school, they really will struggle in secondary school. So it's important in primary school to lay the foundations, and then when the children return to the same topics later on in their schooling, they have something solid to build on and to do well. So we're starting with the early years. That's why we've got 1 at the bottom, and with number bonds for 10, a simple letter puzzle, cryptorhythm, and so on.
So if you are familiar with G10 workshops, then you'll know that you are going to be asked to wear 2 different hats. One is the learner and one is the teacher as you engage with the activities that we're going to have today. So think of the learners that you work with and approach the activities as they would do it. So be a learner. And then switch to your more familiar hat, the teacher hat, and ask yourselves, what do my learners need to know to be able to do this? How would I introduce the activity? How would I organize my classroom? How would I have the learners working together or individually? And do you need any materials that would support their learning? And what questions might you ask to prompt their thinking? Some of the problems that you'll be introduced to today, you might want to try later with learners, and we won't spend a lot of time doing them today, but they're for you to bring into your classroom.
Do, talk, record. Those 3 words sum up a good lesson. And it's something to have in mind when you're thinking of the lessons you're going to teach tomorrow. So the do means the learner's doing, not you as the teacher doing, although you're doing other things. Do as children, the learners should do the activities pretending that they only know, and when you do it, that you only know what your learners know. So think of yourself with a learning hat on. And you're going to talk to other teachers in your group or comment on the chat. And Might learners discover new ideas by doing the activity or reinforce ideas they already know about? And then you're going to record for yourself as a teacher and also in a way that would help learners. But the do talk record will apply in the lessons to what the learners are doing and today to what you as a teachers are doing. So here is a problem. What digit would you add to 33 to get 40 something? We don't know what. And that's why there's a question mark in the units place there. So what is the to do? Well, you have to solve that puzzle. Find digits that you can put in the place of the question mark. And what do you notice? And you've got to write down the answers to those questions. And how do you tackle an activity when there might be more than one answer? So did you spot here that there are several answers, not just one? And so here's another activity for very young learners. All the ways you can get 5 by putting together 2 other numbers. So that flower and the do part of this activity is to either draw a flower or just to look at one and answer, what do you notice? And you can draw your own flowers and put in other numbers there. And this activity calls, of course, for creativity and collaborative learning. So there's 2 examples there of do, talk, and record.
So, as Tony said, we're going to start with the youngest of learners as we go through some of these activities. And you may look at that and go, well, wait a minute, isn't this a sort of pre-algebra question, for young learners? But what we have to remember is that by their very nature, these youngest learners are enthusiastic digit detectives. They're prolific problem solvers and creators, and they're very capable of thinking algebraically. So don't underestimate them. So put your learner's hat on. It'll only take you a second, I'm sure. But so the rules here are you can only use the digits between 0 and 9. Different shapes have a different value, but the same shape has the same value. What goes into the triangle and the square here? Well, I'm sure you've already got the answer. I don't think it took you very long to figure out it was going to be 1 here. But for young children, it's going to take them a little while to get to that. And then they have to check their answer in the second line. Now, card A there was something I provided to students. Card B is a little different. I provided the first line. Now, the triangles here have a different value. So for each set of problems, it's the same rule applies with the digits, and the same digit goes into the same shape, but different for each card. So I provided the 5 plus triangle, and then I asked the class to come up with their own problem and using the answer they got. So what you see 7 minus triangle here was the children taking it quite literally. They created a problem, and I just went round and randomly took one of the problems, put it onto the board with the card. And it's interesting because they've got a subtraction, they've followed it literally, they've got the triangle, and it's an answer unknown, which is always more difficult for students to solve. So A and B, working in pairs, they can come up with these answers. And if you go to card C, Caroline, now A and B prepare them for card C. So I'm sure to you, A and B, even with your learner hat on, didn't take very long. But look, when you look at C, you can see it's quite different now. Now, the thing about this is there are a pair of problems at the top. The squares represent the same number and the triangles represent the same number. And what I said to the students was, tell me, check for understanding. What are the rules here? You can only use the digits 0 through 9, same shape, equals same number. And I asked them to solve this, but I said to them, I don't care whether you start with the square triangle equals 22 or square plus triangle equals 13. It's entirely up to you. So could you take a moment now and solve this? Little different and a little more difficult, I'm sure you'll agree. Working in pairs is very helpful to the students. And I wonder how they got the answers. So this is, while you're perhaps thinking about it, let me just give you a little idea of what I did in the classroom. Again, I asked learners to work in pairs. Once they had solved it, they found another pair of students. So it's an elbow partner to begin with, turn round, find another pair behind you, work in a small team. Did you get the same answers? Where did you start? Did you all start in the same place? You know, what was the value? What helped you figure this out? And so, I mean, you think about the different ways that you might have solved this. How would children start it? Maybe they started with the 13 and listed all of the combination of numbers that could give them 13, and then went to the first one equals 22 and substituted into those shapes. So there are different ways children could solve this problem, very algebraic. Ask the children to share how they started, what was their strategy, what answers you got. It starts to give them ideas about how they can plan to solve such problems, and then share that with the whole class. So the following step after this would be that partners themselves create problems. Prolific problem creators, children, and then you can use those problems to share with the class. They can share them with other members of their team, or they make great homework questions, but they have to have the solution sorted before they share.
The interesting thing about this is you've got two equations, not one.
Mm-hmm.
And the name that we give for this type of problem is they are simultaneous.
Simultaneous equations. Yeah,
And
we don't have to tell our students that at this point, but
no, we don't. But as
no,
teachers,
but
we
that's
know.
what it's, yeah, pre-algebraic work leading to simultaneous equations. And can I tell you something else? And I don't know whether our participants might be thinking the same, but what I found is that the students always wanted to start with 5 in the triangles. I mean, it happens every time. They want to try 5. Now, if they go to 13, 5 plus a single digit, would that give you 13? Yes, it could do. But if you now go over to the 22, 5 plus 5 is 10. Single digit is not going to work in that box. So we know that the triangles have to be more than 5. So even when students get this incorrect, it's a great starting place to start the conversation. So then they can try 6. Well, would 6 work? Well, if you look at the 22, 6 and 6 is 12. So that would have to be 10 in the box. Not going to work. How about 7? 7 and 7, 14. Would that work? Sure would if we put an 8 in there, right? So now let's go over to the 13. If it was 8 and it was 6, would that give you 13? Probably not. Oh, and we've got Caroline here saying she started with 10 and 2. Can't do it, Caroline. We've got rules. It's got to be a number between 0 and 9. It's only one digit. I wonder if there's anybody else thought that.
So what you're describing is what teachers call trial and error. So you try different numbers in there, and if they work, wow, you've got it. But if they don't work, well, you have to try something else. So we're going to move on now.
Okay.
Okay. And of course, one of the things we should be saying is when you do find an answer, then when the learners find an answer, they should be able to explain how they found it. So now we're going to go to a very, very simple exercise, a very simple activity. And if you've got 100 counters or more, you can just fill up this frame. But what you have to do is you have to put on the left and on the right-hand column numbers that add up to 10. So we've got 4 and 6. Now, if we've only got a few counters, we're going to have to just go down the columns, and in the first one you'd put nothing, and in the one on the right you'd put all the counters, so you'd have 0 plus 10. And in the next one you'd have 1, 1 plus what, and give this to the learners to do, and perhaps to do it in a group. So if you gave a group of learners a whole box of counters, they could just fill that up with the numbers that add up to 10. These are number bonds, nice simple activity. But here's one that's not so simple. Can you work on this? Can you find slightly triangles and squares in Marilyn's problem just now? But here we're going to replace the A's by a single digit, same digit each time. We see the A, and replace the B by another digit. So what single digit do you add to itself and then add again that give you a 2-digit number with the same units? There's only one digit, so you could try them all. Then you add 3 of them, and the units digits in the answer is the same as A this time. Okay, of course it's 5, because 5 and 5 and 5 add up to 15. So you put 5 in the units place and replace the B by 1. So here the answer is A is 5 and B is 1. Now just keep that in mind, because we're going to do some more of these puzzles, which are called cryptorhythms. We're going to do some more replacing letters by numbers. So can there be any other number here that it would work? Explain why or why not. Of course, the answer could be you've tried them all. You've tried 1 up to 9, and none of them have 3 of those adding up to a number which has that in the units, that same digit in the units place. Okay, so we're going to move on to another activity. What you see on the left is using beans, and we could have used beans instead of counters in the number bonds for 10. Here we're making little groups of 5 and making the same sort of arrangement so it's clear, so that we help with the counting. So we can count them, the children can count them, 5, 10, 15, 20, and so on. And using the hands, count, everybody raise their hands, and the teacher can go around pointing to the hands, and everybody in the class can count in 5s. And they can make handprints. That's nice, messy for very young children, nice messy activity. And here's the same sort of thing with beans, arranging them in groups of 9, and again counting 9, 18, 27, 36, 45, 54. Lovely, notice the lovely number pattern in that. And that number pattern will come up again later in the today. And here we've got the 9 times table. 1 times 9, and that's 10 minus 1. And 2 times 9 is 18, which is 20 minus 2. And 3 times 9 is 30 minus 3. Ask the learners what they notice there.
Right, so talking about what students notice, and we're always asking them, use your eyes, think about what you see, use what you already know. And like Tony said, use your own digits, your fingers. They're a very useful tool. So never say to students, to children, don't count on your fingers. It's an important thing for them to be able to do. So we've seen examples of subatizing, looking at that pattern, the 9s, the 5s, very important as students move on. And with the 9 3x3 array, moving on into the multiplication tables. And one thing we know is that the 9 times table is loaded with patterns. Tony said, have the students look at this. Well, I'd like to quickly introduce to you a couple of exercises here, or not exercises, activities that children can engage with to help them get to automaticity and familiarity with their tables. And it relies on their hands. So what you'll see from the picture here is got the two hands up. The digits are all their own personal digits, all numbered. And we say to them, okay, so put down your fourth finger. And I always make them, I always have children make these little models of hands, very handy. Put down the fourth finger. And what do you see? You've got 3 fingers in front and you've got 6 fingers behind. The ones in front here are our 10s, and the ones behind are in fact the ones. So put the fourth finger down and you've got 36. Put the 6th finger down and you've got 54. And the more children see this, the more familiar they become. So you can find this on YouTube, gives you all the directions and gives you a nice little video of doing this. But children love it. Let them make their own little handy hands. They draw around their own hands, have smaller versions, whatever. So that really helps them. But does this, the next question you'll always get is, oh, I really like that, but does it only work with 9s? Well, no, it doesn't. So I'm going to give you an example now with 3s. Now, there's a little difference here. If you hold up your hands, what makes your thumbs different than your fingers? You know, typically the learners will come up with, well, your fingers are longer, you've got more of them. But if you drive them back into observing, your thumb only has 1 joint, it's in 2 parts, whereas your fingers have 2 joints, so they're in 3 parts. Very handy for the 3 times table. So going back to our little handy hands, what I have them do is get rid of the thumbs. We don't need thumbs here. We only want the digits that are in 3 parts. And then they number them all, 1, 2, 3, and they go round, ends in 6 to 9 to 12, etc. Turn over and they can do, you know, the numbers on the other side. Now, what you're doing is you're having students or learners, I'm sorry if I keep saying students, it's years of teaching in the US that does that. But the children get to be very familiar with this, and eventually they don't really need to look at their hands, but they're there as a support for them. So again, you can find this on YouTube, but be aware that it doesn't stop at 3. Learning is in your own hands. There are ways to find the 6 times table, 7, 8, 9, and 10. So we know the 9, but they're all there for you to explore and share with your learners.
Now,
So,
oh, yes, we've got some children's work coming up.
yes, we have indeed. And I just wanted to share this very quickly because the important thing is use your eyes, you know, use what you know. And students, having been doing a lot of work with the 9 times table, I wanted them to look at those patterns that we saw in Tony's slide earlier, and I wanted them to explore them. And I'm sorry this is not a very good picture I took of students' work, but I asked them to try and put them into teams, small teams. I think there were 5 in each team, and they had to talk about the patterns that they could find. So if we look to the left of the screen, what you're going to see is the pattern that we all know, that, you know, students started to write out, you know, 9 times 1 is 0, 9, 9 times 2 was 18, etc. Then they noticed when they got to 9 times 5, 45, that a little change happened. Because when they got to 9 times 6, it was the same digits reversed. So instead of 45, it was 54. And then they looked back and saw that 9 times 7 was the same as 9 times 4, but again, the digits were reversed. So this is helping them, that they know that the digits always add up to 9. They know there's reversal of the digits, and you can see them exploring that pattern on the left-hand side. On the right-hand side, these children already knew their tables quite well. And so they went along to see if they knew there was a pattern through the 0 times 9 to 9 times 0, or 9 times 10, would that pattern follow with the through to 20, from 11 to 20, and from 21 to 30? So allowing children to explore these patterns at the level they're at is very helpful. And they were very excited to find out there were 11 of the answers had 2 digits, or 1 or 2 digits. They got into the hundreds on the 12th. And then because they started with 0 times 9, and then they found there were another 11 that had 100 as the answer. And then they went through and they found there were 11 in the 200s. They were very excited about that. But here are students finding patterns for themselves. And they found that the rule of reducing the answer always to 1 digit always gave them 9. And realize that's going to be a check, which we'll see later on, is going to be a check to see if you've got the answer right, to multiplying any number by 9.
So now we're going to go on to think about some more digit detective work. And here you're going to put, you're given some numbers, 6 numbers, and you're asked to put them in the boxes to make an addition sum that adds up. So how are you going to do that? So I'm going to be quiet so you can think, and I won't interrupt your thinking. Have a go at that one yourself. Now here's a clue. You've got to have smaller numbers adding up to the bigger numbers. So maybe you've got to put the bigger numbers in the answer. Now, what I'd do if I was teaching, now, what I'd do if I was teaching children is to say, look around the class, and if I saw that somebody had completed this successfully, I would ask that learner to provide the clue instead of giving it myself. And then that would help the other learners. Now, here are 2 more cryptorhythms. And here, just like the one A plus A plus A equals BA, which was 5 plus 5 plus 5 equals 15, we've got something similar. Now, the clue here is to think about the A in number 2 and the Q in number 3. I think you'll quickly be able to see what those numbers must be. Remember what's happening. You're just adding numbers to get answers that are have to be 100 and something. So here are the answers for number 1. So you can either put 65, make the answer 65 or 56. You've got to put the bigger numbers in the answer because you've got to have the other numbers, other digits adding up to, so 2 and 4 add up to 6, and 2 and 3 add up to 5. And you haven't got just one answer, you've got 2 there. And what about these? Now, if anybody's got an answer for these, you can put them, these cryptorhythms they're called. There's the answer for the first one. A must be 1 because you can't have anything bigger than 1 if you're going to add 2 digits that are 9 or less. Carrying number must be 1. So if then you've got 1 and something, we need 1 and 9 to have anything to carry over. So A must be 1 and BB must be 99, and similarly Q must be 1. Does that help you to finish these? There we go. 99 and 1 give 100. So C is 0, A is 1, and B is 9. And again, of course, the Q has to be 1. And if you put the 1s in, it's very obvious that P is 9 and R is 0.
And Tony, can I just add, I'm just looking at the chat here, that Janita has also added to number 1 that 34 plus 22 is 56. So she's moved some of those digits around to get the same answer, 56.
Oh, well done. Lots of answers here. 34 plus 22 equals 56.
Right, now, this follows along from what we've just been doing, but it's interesting that children get thrown a little bit. You know, it's easier to see that letters stand for numbers. It's sort of a code that maybe they're used to. But once you put symbols in, it gets a little more challenging for them. But it's very interesting, and it's the same thinking as Tony said. So a little different here because we've got 3 sets of numbers, all 2-digit, giving us a 3-digit answer. The colored shapes must be, it must have each of the shapes, or the same shapes, for example, the green circles must have the same digit in, pink rectangles and the blue rhombus must all have the same numbers. But it just throws children a little bit, but now they've got this extra layer. So put your learner's hats on again, see what you can come up with for this. Well, again, let's go back and have a think of those clues from before. So we've got an answer that's in the hundreds. So what do you think it will be? Will it be 100, 200 or more? Think about those circles that you've got in the first line. And what are you going to do to end up with a circle and a rhombus and that pink square in the ones place, the units place, to give you a pink square? It's very intriguing, this. If you've got an answer, could you explain how you arrived at it? And maybe if children are really stuck because they just find this too challenging, we can extend the clues that we give to them. So how about telling them, and we would reveal these one at a time. Okay, so let me help here. The digit in the hundreds place is a 1. And then the circle and the rhombus add up to 10. And then see if they can come up then with what the rectangle is going to be. So here we've got the answers. I didn't see in the chat anybody coming up with it, but it's a great challenge for your learners to engage with. Should we have a look at another one? Oh, here we go, more cryptorhythms. Okay, so now we've got 2 addends, both of 3-digit, one that's going to give us a 4-digit answer, and one's going to give us a 3-digit answer. How are you going to tackle this? What clues do you think you could give to the learners? And here's a way to start them off by telling them how many possible solutions there are. So the first one has 7, and the second one has a huge number, 16. So what learners think straight away is, oh, I'm probably going to be able to get one of these.
I like problems like this because it gives a lot of learners in the class an opportunity to give an answer. And
Yes.
you don't need to finish it the same day. You can put it up on the wall and then say, anybody find another solution, we'll add it to our poster, and we'll add that until we get the full numbers for all 16. And then if somebody comes up with an answer, you can really congratulate them, and because everybody's been hopefully looking for an answer. In fact, you can make it homework to go and see if they can find another answer.
And I'd like to add to that, Tony, because there's something that I've done with these problems that I've used from the Enrich site. I've made a poster, large piece of paper. I've put it on the wall. I've written the problems on, and learners have come up and they've written on it what their solution is. And so we can see how many different solutions that they come up with. It's up there for people to check. If they come up and find somebody's already come up with the same solution as them, they put a check mark next to it. And then we can count how many people arrived at, the same solutions to these problems. But it gets the whole class involved as well that way.
Develops the teamwork, doesn't it?
Yes, absolutely. So should we have a look then? And what clues could you give learners? We were asking, I don't see anything here, but one of the things that you might think of is giving them a partial solution. If they're really stuck, maybe just pick out one. Maybe it's the O, the letter O, that you give them the value of that and then see what they come up with. But remembering that there are multiple solutions here. So whatever we give them is only one of the, only going to prompt them in one of those solutions, or maybe more, but not all of them. So here are the 7 possible solutions to 2 plus 2 equals 4. And the 1 plus 1 gives you 2. We've put up just one solution there. Remember, there's another 15 that you and your class can work on. Now, as a follow-up to that, typically I always ask students the same question. Can you now come up with your problem? And they can work with partners, they can work in a small team to do that. But you have to be careful here. This is one thing I've noticed, and it's rather funny. They'll come up with 3 plus 3 is 6. And you go, wait a minute, you're adding, 3. How many letters? 5. You're adding 2 5-digit numbers to come up with a 3-digit answer. Be very careful, and point them in the right direction here. But they get a bit carried away with, 2 and 2 equals 4. But I do give it to, ask them to come up with their own problems that must have a solution with it for their homework. They would just have to create one. And be careful, beware when you do this. You might be landing yourself in for something. So if we could have a look at the next slide very quickly. Right, this was actually a problem that a student brought to me the next day. And he said, I worked on this with my dad last night, and I remember Devon giving me this, and the problem is to the right. And I thought, oh, interesting. So like the good teacher I am, I went home and I did my homework, and I came back the next day with my answer that Devon, checked for me. And then I asked the class if they could solve it. I said, this is what Devon and his father brought to me. Can you solve it? Now, to some students, they tackled it straight away. But to other students, it was a challenge. And so for them, I moved them into a different group and I gave them a partial solution, which you can see here to the right. So this is what I mean when I say give them partial solutions to help them along the way.
Well, we've got another partial
Yes.
solution for this one. So here, first of all, would you like to do it? Would you like to do this substitution code and see what goes in there? So F is 1 and O is 9. And what does this reveal? If you've got a copy of the worksheet, you can do it on that. We've got some solutions here of the 1 and 1 is 2. Okay, well done. And here's what you get for this substitution code. And look, it is actually some 2 4-digit numbers. And if you add them up, you'll see that the answer there, it makes that a correct 1994, a very important date in South Africa, plus 6533 is 8,527. And that's correct. Now, that's just one solution for this foot plus ball equals game. What you've got to do there is to replace, as with all the other similar cryptorhythms, you've got to replace the letters by numbers. And here there are 224 solutions. So we can do what Marilyn mentioned, is put a poster up on the wall and have people put the solutions in. But they're going to have a system for arranging them. Otherwise, it will be really hard to keep track of whether a solution's been repeated there. So finding a good system is an important part of doing that. But that one I found has been quite a popular but quite hard teaser. So you can give them some help by giving a partial solution here. What if you've got those numbers? What would you have for B, A, L, and L to complete this solution? So that's the football problem. And of course, if you've got 17, 18-year-old learners who do some programming, there's some quite a simple computer program that you can write for the computer to find all 224 solutions. And if you look on the Aiming High website, you'll find the computer program is there, or a sort of pseudocode for it, and you can put it into your whichever language you know. So if you've got some learners who are doing computer science or IT, then they might be able to do that. So now if we look at this digit detective problem, what's the difference between a digit and a number? We've been using these words. It's important we do know the difference. So here the number is 12, and there's another number 19 there. And the digits are 1, 2, and 9. They're the single digits, a digit is a single number, whereas a number is, maybe hundreds and tens and units, or it may be thousands, hundreds, tens and units, or it might be in a decimal form. But each place in that system is you put in a digit to make the number. So we'll start with simple calculations, so learners will find it easy to explain how they were thinking about the problem. So what's the missing digit here? How will you find the missing digit? Where did you start? Why? In class, share methods with get the learners to share methods with each other and explain how they found the answer. Anybody want to suggest how they found this? I think we all know the answer is 7, but how would you get the 7? You just knew the answer, perhaps. Or you subtracted the 12 from 19. So why did you do that? Or you might know that 2 and 7 add up to 9. That's what you need if you add the units digits there. Or you might have some other method. And what method would you use for these two examples? So can you replace the question marks here to get something sensible as an answer. So maybe this subtracting method is going to work for the 3-digit numbers as well as the two-digit numbers. So if you subtract 150 from 257, then you'll have your answer there, which is 107. And for the other one, well, you could have quite a few different answers here, perhaps. Or maybe you couldn't have any at all. 8 and something is what? Okay, so digit detective. What do you do as a digit detective? Imagine you're a detective and you have to discover what digits the question marks stand for. They can be any digit from 0 to 9. Or they can be the same digits and different digits. So we don't have this rule now like we had with the other with the cryptorhythms. The question marks are just unknowns and they can be any digits. So how are you going to find the missing digits? What do you notice? You've got to notice something about the arithmetic there. How many solutions are there to the calculations? There may, in fact, be no solutions. And what clues did you use to help you work out your answer and explain why this happens?
Just on the first one, so you've got question mark plus 8 is equal to, would that then be a double-digit answer with the 2 in the tens column?
Ah, now that's a good question. No, there'll only be a single digit there. But remember, what I said is that there might not be a solution, or there may be one solution, or there may be many solutions. So,
But it's not necessarily a double digit.
well, if it would have 2 question marks if it was a double digit.
Oh, so it's not 2 and then digit. I'm not understanding. So it's anything from 0 to 9 is going to be for that question mark on the left, plus 8 is equals to 2 question mark, which is replaced by any digit from 0 to 9.
Yes. So can you have a single digit added to 8 to give you 20 something?
Oh, yeah, no, you can't. Because the maximum would be 9. 9 plus 8 is 17.
Yes.
Same for the second one, I'm thinking. In excess of 20, you wouldn't get an answer of 1 in the tens column. Again, is that double digit?
So if you had 20 something and you added 4, you would get either 20 something or 30 something, wouldn't you?
Yeah.
So
never with the 1.
that's right.
Yeah.
And in
And-
mathematics in general, when you're looking for a solution to an equation, you can either have no solutions, one solution, or many solutions.
Yes, correct.
And in fact, there could be infinitely many solutions. Now, the questions that are often set to, or normally actually set to children in school have one solution, and they run away with the idea that there's always one solution if the teacher just sets that sort of question. So actually, it's much more thought-provoking to let them know that there may be no solutions, there may be one, or there may be many. And in this case, we've got some examples.
The third one I'm thinking, question mark could be 7, 8, or 9.
So we've got 3 solutions there.
Yeah.
And of course, if it was 6 or less, we wouldn't have 40 something, we'd have 30 something.
Correct.
So
Thank you.
great, well done. So as we've just been talking about it, if you were there and heard, the most we can get is 9 plus 8 is 17, which is less than 20. So that's impossible. There can't be a solution there. And similarly, 20-something plus 4 is in the teens, you know, is 1 something. There's no solution because it has to be at least 20, and by adding 4, you get a number that's greater than 20. And in the third case, we have got 3 possible solutions. Don't get a solution if you add any digit less than 7 to 33. Because if you want an answer that's 40-something, you can add 7 to get 40, 8 to get 41, and 9 to get 42. So you've got 3 solutions to that one.
So, if you were here during the break, there was a very interesting conversation between Tony and Janita, and they really got at some of the objectives here. What is it, you know, we're trying to do? Well, what we're not trying to do is to provide direct instruction with these activities, but rather, and we're not even demonstrating methods to arrive at correct solutions, but we're trying to get the learners to arrive at their own way of explaining these and to investigate. So our objective really is to provide opportunities for learners to observe, to think, and to use what they already know and to discuss and hear alternatives from each other. And in doing so, they're building their academic language, their way to describe mathematics as well. So in keeping with that approach, it does change the teacher's role. So, you know, we're not going to give them answers, but we're going to give them encouragement to go back and to look for more solutions. We're going to be asking questions that prompt their thinking, that force them to look at these numbers again and use what they know. As somebody said in the chat before, they needed to use what they know about inverse operations to solve some of the problems that we've presented. So the teacher's role changes. You're not the sage on the stage, but you're the guide on the side, pushing children, asking them, are there more than one solution? How many solutions can you find? If they come up and say, is this the right answer? You say, I don't know. What do you think? Can you convince me you're correct? So it's driving them back always to question their own thinking and what they know. So our objectives are quite different here than what we would normally see in a teacher-directed, instructionally based lesson.
Well, in AIMSEC, as you know, everybody has been involved somehow or other with what we've been doing over the years. We're having activity-based learning. So we don't have teachers who tell the learners to do this and do that and talk most of the time, but teachers who give the children activities and base their lesson on what the children do themselves.
Yeah, and there's a nice expression for that, Tony, which is hands-on, minds-on. That, you know, when you've got your hands on the problem and you're doing it, your mind's on it as well.
So we're going to move now to some more questions to do. Here are 2, one adding, one subtracting. When you find answers, or you give this to your students to do and they find answers, you ask them, what clues did you use, and explain how you solved the puzzles. You may get the learners to do this in groups. So I'll give you some more. We're going to have more time to come up with the answers. I gave you a little time there to think of the answers. Now here's one bit different. Here we're finding the largest value if we have two two-digit numbers? What would be the largest answer we could get? We've got to explain why it is the largest, and we've got to find then not the largest but the smallest possible total and explain why that one is the smallest. And then the last two questions are multiplication and division. Those are on the worksheet if you've got a copy of the worksheet. You can have a moment or two to try those. And then we'll move on and give you the answers. Now, these sort of questions are certainly suitable for upper primary, age 7 to 11-year-olds, and secondary as well. In fact, if they haven't had lots of these when they were younger, I would even give this to year 10, grade 10. They're nice problems. So let's look at the first two. This has solutions 326 plus 57. And the clues? To get the units digit, you must add 7 to the 6 to get the 13. And then you look for 1 plus 5 plus something to make 8 to find the tens digit. Okay. Now this has a solution 893 minus 78 is 815. And the clues? You must find a number to subtract from 13 to get the units digit 5. So that's going to be 8 from 13 that gives you the 5. And then you use inverse operations. If you've got two numbers adding up to a third number, then you subtract one of them from the third number to get the other. And if you've got a subtraction there, in this case, I would add the two-digit number to the one on the right to get the other number.
So C, now the question C is a little bit of a change of pace here, isn't it? Or at least a change in thinking, because we don't know what these digits are. We don't have anything, a place to start, apart from what we already know. So same things apply. We've got 2 question marks plus 2 question marks, each of which stands for a digit. Each of the question marks stands for a digit. What would be the largest total? So I'm going to give you a moment just to see if you've got your answer for C. Now, what question might you ask here of students? So here's a solution. It's 97 plus 86. But what questions could we have asked as clues to lead students to that solution? Well, what we know is we need the 4 largest digits we've got. So it's going to be 9, 8, 7, and 6, which means that we can put these, because what we know about addition and commutativity, we know that it could be either 96 plus 87 or 97 plus 86. That's important to bear in mind as we move on. So the answer here would be 183, irrespective of which way we do this.
In this particular problem, although not in the others, they have to be 4 different digits.
4 different digits. And with that same idea in mind, to find the smallest total, it's going to be 4 different digits. And they're going to be 0 to 9. And that's perhaps what we need to say, you know, could be 0 to 9. And so the smallest digits this time, not the largest, are going to be 0, 1, 2, and 3. And how can we organize those? Well, that 0 is not going in the tens place. It's got to go into the ones place. So it could be 10 plus 23. Or it could be 13 plus 20, 0 in the ones place again, in the units place, both of which give us the answer of 33. Now, that might be doable for the students because it's addition and they can come up with the different solutions because they know the order of those tens and ones. Not going to make a huge difference. But if we go on to the next problem, it's not going to make any difference, never mind a huge difference. But if we go on to D, here's an issue. We've got the same questions, but this time we're not looking for a sum, we're looking for a product. So what 2-digit factors of the product are we going to come up with for the largest product here? Now, instantly the learners will want to apply what they've done in C and think about the ordering of those digits. It's a little different here, isn't it? So we've got 9 and 6, and we've got 8 and plus 8 and 7. Does it matter the order that we arrange those digits, what numbers we make from them? So we can't repeat a digit, but if we look at the 2 possible answers, we find that 96 times 87 gives us a larger product than 87 times 96. Right, so, you know, it's a difference of 10 here. Why? Why is the question for the students? And did you realize that you're going to get a different product here? So if you just click on that, Tony, let's see how we can help students, how we can guide them towards the solution here. If we use the lattice method or a grid to plug in partial products, and we've already talked before that sometimes giving partial answers is a good way to help students. This is bringing us back to partial products here. So if we look at 80 times 90 and 90 times 6, 80 times 7 and 6 times 7, we're going to get the answer as we see in our first chart down in that lowest right-hand cell. We've got, when we add our totals here, we've got 8,342. When we organize those digits differently to make different numbers, 96 times 87, what we find is that if we slide all the way over in our observation to the right-hand column, we'll see that those 2 partial products are going to give us 8,352. So if we ask students then to explain this, or learners to explain it, put it into their own words, then what we're going to try and extract from them by the questioning we use is to get to the largest product, we have to multiply the largest units digit by the largest tens digit. And we can see that in this grid method. So actually here, our ones or our units are going to be very important. So units here are important. They give us different solutions to those problems.
And interestingly, here Marilyn's been talking about this grid method or area method for multiplication. And it's one that makes so much sense that I think it's one that should be introduced as a method of multiplication for all classes when they learn how to do multiplication.
And can I just say this, Tony, if we want to think about multicultural mathematics, This is exactly how it is taught in some countries. And so this idea of, making sure that you've put a 0 in the, units place and all of the rest of it, it becomes very evident why we're doing this. So this is the way it is taught in many countries.
Yes, it's a logical way of doing it.
Yes, it very much is. Now we've got the division problem, which after that multiplication actually seems quite simple. So what's going to go here in where the question mark is, and it's one question mark, so it's going to be, a 1-digit answer. And earlier, somebody in the chat, we didn't mention it, but they said about using inverse operations. So here, what do we know about division? Well, it's repeated subtraction. So what we could do to solve this, and this goes back to being able to have younger learners doing this, we can see how many times can we subtract the quotient, 272, from the dividend, right, 816. Or we can say, what do I multiply by 3 to get 816? So there are different ways of looking at it, but repeated subtraction is one method that many learners will use for this, or to just divide 816 by 3 and you get your 272. So our missing digit there was 3. So again, why do the activities? Well, what we want is to develop a deeper understanding of inverse operations, as somebody noticed in chat, to give students the opportunity to use what they know and apply what they know about place value, to challenge them as learners, not by saying, oh, I know you can do this, but can you be a good observer? Can you be a good detective? What are the skills of the detectives to solve a problem or a puzzle? And what can you, what are you using here? You're using your number sense, logical thinking, and to tell students this, you're being great problem solvers, great digit detectives, because you're using what you already know. Look how much you know is the thing. So what we see in red are generic skills that they're going to be able to use across the board. And when they work in pairs, they're going to have to explain what they're doing, or explain to the class, or explain to a larger team of 5 or 6. They're really developing communication skills. And this whole idea about the development of academic language is huge at the moment in education. And we are giving them the opportunity not to just to receive the language, hearing it from us, but to produce academic language as they communicate with their partners. So handling problems that have no solutions can be a bit of a challenge, or realizing that, yeah, you got one answer, but guess what? There are many more. Can you find them? Multiple solutions. And it helps students be flexible in their thinking when they're doing this, and telling them that they are really strong mathematicians because they have the power to analyze and interpret informations. So self-confidence, self-concept of themselves as mathematicians is all helped with these type of problems. It really boosts self-confidence. And as I said, anything in red here are skills that are not just applicable to our problems and activities today, but they're generic across mathematics and beyond mathematics. The type of skills that they're going to be using in science and in problem solving and other curricular areas as well.
Not just in school.
And
These
not just in school. No.
These are the extension.
Yeah.
The essential skills
Yes.
they're going to need for adult life. And because of AI now, a lot of jobs are going to be no longer available for anybody to do those jobs when our learners in school grow up and in the big wide adult world, they're going to need these sort of skills which apply across the board in many types of employment.
Yeah, and another thing adding on to that, Tony, is when employers are surveyed about what skills do they want their incoming, workforce to have, teamwork comes up at the top of the list all the time. So having students work together and not in isolation is not only about communication skills, it's learning how to work in a team.
Okay, well, I'm going to talk about the magic of 37 because I think this is very pretty. And this is the first of a few problems that we have got for you, which involve rather attractive, I think they're attractive, number patterns. So here we've got 37 times 3 and on the left and 111 on the right. So what this is for you to do, number sentences comes on. CAPS is the name of the curriculum in South Africa. It comes into all different countries into their number work, into their curriculum, number sentences. So make these sentences complete by putting the right symbol in the box, either a multiplication sign or an equal sign. And look at the numbers that are coming out of this, the statements and the patterns. Carry on then beyond this. And what pattern do you notice? I would then say to the students, I'm saying to you now, write down everything that you notice.
Hi, this is Kemi. I meant it's like a multiples of 3 at both stands. Starting with 3 times 1, you get 1, 1, 1. 3 times 2, you get 6. So 37 times 6 is 2, 2, 2, and you keep going on that way. That's the pattern.
Yes, and of course on the right-hand side, you've got a repeated digit, but you're going up each time to the next digit. So you go up from 222 to 333 to 444. And the question is, after 999, you're going to go into the thousands, but what happens then? And so there's quite a lot of interesting ideas in this magic of 37. Now here's another pattern that's going to emerge. How would you find out here what these question marks stand for? Got to replace the question marks to complete the calculations. Give you a minute to do that. So the solutions are 98 times 9 plus 6 is 888. And the other one, we get 88,888,888 on the right. So the first number here is quite a big number. It's 9,876,543. And the interesting pattern there, got 9,876,543 going down, times 9 plus 1 gives you your 88 million and so on. So what's happening here? We complete these calculations. Use a calculator if you wish. You'll begin to see how this pattern is going to emerge, and we'll have a look at it, the whole pattern, in a minute. And here actually it's all number work, but we're really doing algebra, because we could think about this as 9x plus 5 is 8,888 and find x. But by replacing the question mark, we're actually making it look just like number work and solving digit detective problem. And here, what do we have to multiply 9 by to get 888,888,888? Well, here we can 0 there. We're not going to need to do anything with that, but we are going to divide this number on the right by 9 to get our answer there. And you could use a calculator if you like. So there are the solutions. What patterns are we seeing? So if we look at this, these are some of the calculations that you've just been looking at and doing. And how did we find the missing digits? And how can we explain how this pattern comes? All those 8s on the right. And there's the full pattern. It really is rather a pretty pattern. 9 has, we looked at the 9 times multiplication table earlier, and this consequence of the digits going up in one at a time or going down one at a time has this effect in this pattern. It's really nice. And Marilyn will talk about another pattern here.
Yeah, and it really segues into that last one, which I really like, because it does tie back. And when Tony talked very early on in like the second slide about a spiraling curriculum, you can see how what students are learning very early on is being brought into solving these problems and looking at that pattern of how the 10s and 1s, you know, change with each of the answers. So now, based on what you've just seen, where the answer is 888, you know, 8's repeated all the time. Can you do some calculations here to explain how the patterns here change? So you might want to do that by looking at the first couple and see if you can establish a pattern. You might also want to try and think about how you would explain this by multiplying by 10 minus 1. So, you know, 12 times 10 minus 12, for example. I'm going to ask people to just solve those first couple, first of all, before we look at this pattern, that's this answer that's flashed onto the screen. But you can take a look at that to help figure this out.
Well, the first two are very easy, aren't they?
Yes, they are, but it helps you figure out a pattern because you've got the answer, you know, you've got answers straight away that have something in common. And if you look at the third one as well, that perhaps gives you, but let's take a look by looking then. I mean, have you got the pattern? Do you see what's happening here? Do we have a series of 8s in the answer to these problems, or is it different digit? Well, you can see by the answer that we've posted here for where are we? 12,345 times 9 plus 6. But the answer is going to be 111,111. So where does that come from? Well, we can certainly do it by doing the multiplication and adding the number. One of the things that we need to look at is that number as well that we're adding all the time. And think about this, see where it comes from. I mean, there are two different ways to look at this. And it was very clear on where we got the answer of the 8s, why we were adding this additional digit on at the end. But if we have a look here, we can see that if we do 12,345 by 10, we get 123,450. And then we can add 6 to that. We can move that 6 along and say, okay, we can get this added in at this point. And the answer will give us the 123,456. And now we subtract one of those numbers because it's 10 minus 1. So we're going to subtract the 12,345 and we arrive at 11111. Right, so we've got this pattern of ones that we've already seen in 0 times 9 is 0, plus 1 is 1, 1 times 9 is 9, plus 2 is 11, 12 times 9 plus 3 is going to give you 111, etc. So we've already established the pattern, but here we can see how it arises. And maybe we can see when we have this 6 on, or 5 or 7. If you go click again, Caroline, if you don't mind, and have a look at this other one where we've got an arrow here. Did you work that out without doing any calculation? Right? So the answer here is 111,111,111. Okay? And if you look at, we're adding 9 on, how many ones were there in the answer? Well, if we look now at where the answers are, I need to just move my screen a little bit here. If we look at where those answers are, we can see that number that we add on is giving us a clue to how many digits we're going to have in the answer. Is it going to be 1, 2, 3, 4? You can see that pattern. And it intrigues children because they're able to use what they already know about the 9 times table. They, as Tony said, they could solve this algebraically. But also, it tells kids this, and this is why the picture of the pyramids are in the background. They're engaging with an activity that has intrigued and fascinated mathematicians, or just ordinary non-mathematicians, over time, because the Egyptians worked on this, as has every generation since. So having students look at these traditional patterns gives them the opportunity to use what they already know. So we've got some answers popping in here, not quite sure what's coming in. So these are great patterns. Is there anything you would like to add to that, Tony?
Well, I just yes, I just think these are very
Things pop
pretty.
up a bit quicker
And
than,
if you want more material with these patterns,
yeah.
you can go to the Aiming High website, and we'll give you the links later. Now we're going to move on to another activity. Again, it's all about numbers, and here I would say to the class, and I'm saying to you now, just close your eyes and think of a number.
2 numbers.
Okay, now think of 2 whole numbers under 10. So think of a number trick. Now what I want you to do is to think of 2 whole numbers under 10. Now just take one of them and add 1. Now multiply that answer by 5. Add 1 again. Double your answer. Subtract 1. Add your second number. Now add 2. Double again. Now subtract 8. Halve this number and tell me your answer. Now, I'm going to be able to work out both your numbers very quickly. And how am I going to do that? Because there was a lot of adding and multiplying and doubling, and Whitney went through that. Now let's do a different pair of numbers and repeat the process. And what I want you to do is to try and find a good explanation of how the trick works. So we'll go through it again. But now think of 2 whole numbers under 10. If you lost your way in the last one, think of the same numbers. But if you went successfully through the whole process last time, you can find two different whole numbers under 10 this time.
Maybe we could even suggest what those numbers are, the digits are.
Well, we could, yes.
It could be a 6 and a 3, for example.
Okay, let's do the 6 and the 3. Now you take one of them and add 1, multiply by 5, add 1 again, double your answer, subtract 1, add your second number, add 2, double again, subtract 8, halve this number. Now, tell me your answer, and I can work out both your numbers very quickly. Okay. Did you do it then, Marilyn?
Well, I think that before they halve the number, no, when they get to the end, after they've halved the number, I should say, I think people have either got for their answer 45 or maybe let me think, maybe 72.
So
I
if
think
you got
that's-
45, all right, I think your answer, your two numbers were 3 and 6.
Yeah.
And if you got 72 as the answer, your two numbers would have been 6 and 3. So it's 3 and 6 with those two answers.
yeah,
45,
some
70.
people may have taken 3 as the first number to start with. Some people may have taken 6 as the first number to start with. So, but we know at the end what those digits were that people started with.
So anybody like to try this out?
Yeah, because I know somebody has got the answer 36.
Yes.
Mm.
Adetunji, Samuel Victor, you got 36. Well done. And those two numbers of 3 and 6 is what I think you meant, starting off with the numbers we started with. Okay.
So let's, can we
So-
take a look? Yeah.
So you've got 6 and 3. What happens is you have 6 plus 1 equals 7. And then you multiply by 5 and you get 35. And then you add 1 and you get 36. And you double your answer and you get 72. And you subtract 1 and you get 71. And then you add your second number, which was with 3. And you get 74. And add 2, you get 76. And you double 76 is 152. Subtract 8 and you get, if you subtract 8 there, you get 144. And then if you halve that, you get 72. And what did I do to say that the numbers were 3 and 6? Now, of course, they were suggested by Marilyn, so we knew they were 3 and 6. But whichever two numbers you chose, I could have found out what they were. So this is a trick. So different people in the class will choose different numbers. And if they just tell me the answer they get to, whatever it is, I'm going to immediately be able to say what the answer is. And in the thought bubble in the middle there, it explains how. So all I do is subtract 9 from the answer that they have, and then the 2 digits that come up there, 72 minus 9 is 63. So I know that the 2 numbers that they started with, 2 whole numbers under 10, were 6 and 3. So why does it work like this? So can we find a good explanation of how the trick works? And learners will love this trick, and they can try it on their friends or their parents, and it's really a magic trick, isn't it, if you don't know how it works? But then we can ask them to find a good explanation of how it works to work in a group, to maybe think about it over time and come back with an explanation tomorrow. What is the explanation? Well, here it is. It's algebra, of course. Supposing the numbers are a and b, and they could be anything, and then the first instruction was to add 1, so we get a plus 1, and then we multiply by 5, and we get 5a plus 5, and then we multiply by 5 and we add 1, so we get 5a plus 6, and we double that answer, so we get 10a plus 12, and we subtract 1, so we get 10a plus 11, and then add the second number. So if the second number was b, we've got 10a plus b plus 11 now, and add 2, 10a plus b plus 13, double 20a plus 2b plus 26, subtract 8, 20a plus 2b plus 18, subtracting that 8 from 26, and then halve that, we get 10a plus b plus 9. So here we are, take off the 9, and we've got 10a plus b. So I know the number has digits a and b, because 10a plus b will have a in the tens column and b in the units column, and I know what the 2 numbers were. So that's a way of explaining the answer here, which uses some algebra, and it's a nice way to.
It is, and there are so many of these problems, right, Tony, that we can use other ones where it's always going to be the answer 1, so it was going to be the answer 4. But this is nice because people get different answers, and you can still figure out what their starting digits were. And what they see in this is that digit that you are adding on, in its own way, is a red herring. Because, you add 1, then you've got 5, then you've got 6, and then, at the end we end up with 9, we subtract that 9, we get rid of it, and we're back to 10 times one of the original numbers, and, one of the original numbers, b, in this instance, remains unchanged. And I think showing it to them algebraically shows them that mathematics always is always ahead of magic, or magic gives way to mathematics, and they just have so much fun here doing these. And again, coming back to what I always say, have the students write them. They love to write these, and they have to work out algebraically how this is all working, and it's something they thoroughly enjoy. Whatever their age, you just vary the directions, but any learners can, the number of steps and the directions in the steps can vary, but magic numbers intrigue them.
Yes, and help them to be creative. And I would give this as a task for pairs of learners to work out their own trick, to create their own trick, and then give them the opportunity to try that out on the class. So now we're going to come to a summary, and I think it's really a good way to finish any session, to look back at what you've been doing and to think about what's gone into today's session and what sort of thing have we learnt.
I do have favorites. Anything that involves number 9, I just love working on with children, remembering primary, early secondary years, more the age group I work with. And they are so intrigued that it's infectious. I mean, I just love anything that involves 9. And also magic numbers, because when you come up with the answer, I mean, they think you're so cool. They think that, how did she figure that one out? And so you instantly go up in their esteem. But to get them involved when they're looking, that they're creating questions, to me is the important thing, that they're thinking about it, they come up with the answer, people solve them, and they mark them. You said this question, is this person correct? So they put them in the role of teacher. So anything involving 9 or the magic numbers, and all of these activities are great, because I think you can really see how youngsters can even work with some of these questions that look like they're specifically for older learners. But even with the pyramids, the one that we've got on this slide down in the lower left corner, I mean, you can ask younger children to solve up to 123 times 9 plus 4 and begin to establish patterns. So it's the fact, I always call them elastic problems. They've got these sides that move, and learners at any stage can engage with them. Could I just pick up and Gladys saying, very interesting session, it'll be worse with learners. I mean, I don't dispute this at all, but it's taking that first step. You know, you don't have to do all of these activities, but choose one and see how it goes. And it's about what I said earlier, that we have to reconceptualize our own, you know, role as the teacher. Don't think you've got to have all the answers. Push it back on the children. Can you convince me of this? Were there more answers there? What was difficult about it? What do you know that's going to help you here? You know, every journey starts with one step. So just take one step.
Well, I think it's really important not to underestimate your learner.
Yes.
Because that is a real problem for example, in South Africa. Now, South Africa performs one of the worst in the world at school mathematics. I don't know whether you know that. And it's something that has really made my heart ache over 20 years I've been working in South Africa, because I think the teachers do underestimate the learners. The children in South Africa are just as clever as children anywhere in the world. And so when they have these international comparisons, South African children should be doing well. Why are they not? Now, don't blame the children. I don't blame the children. I don't blame anybody, really. But what I'm saying is, the problem is, I think that the teachers underestimate the learners. They really do. And what is important is not that children can get right answers to the sort of question that they're familiar with and pass the test. It may get them through the test, the exam, but it's absolutely useless in real life just to be able to get right answers to calculations. Why? Why is it useless? Well, there may be odd occasions that you might get the wrong change given to you in a shop or something like that. Maybe you need to be able to estimate whether what you've got is the right amount of change. There are times when being able to do the arithmetic is important, but for a job, absolutely not. Because, and why? Because computers and calculators will do the calculations much more accurately and quickly. With artificial intelligence, a lot of the things that our schooling prepares us for are actually useless in real life. What is useful is the skills that we've been talking about, those generic transferable skills. That's what's useful. And being able to do problem solving. That is not to solve problems that the teachers taught you how to solve, but to solve problems like these.
Mm-hmm. But they've got to be given the opportunities. And so that takes me back to, you know, try some of them. You don't have to do them all, but take a first step. And you'll find that when the students are, what I said before, you know, hands-on and minds-on, they want more of those type of problems, and they do rise to the challenge. And the other thing I was thinking of is that it teaches them to work with partners and to communicate and to understand other people's perspectives. But also on several of these, we asked, where would you start? How do you begin to do this? And so it's developing an action plan. And I think that goes along with what you're saying, Tony. It's not, you've got to have action plans. Where are you going to start to solve this problem? Because if you're taught just an algorithm and suddenly it's got 5 steps to it and you forget step 3, you don't know where to go. You know, it's like, right, can't do any more of this. So, you know, move on to the next question. But if you have a plan, it really helps guide you what you already know that's going to help you move along with this problem.
Now, what you've got to think about is what's been happening in this session is that we have quite quickly, in a short time, a couple of hours, we've talked about the sort of number work that you could do in 12 years at school, okay? And we've done this, examples of this work in number work in just
120 minutes.
Yeah, yes.
Yeah,
So
10 minutes per year.
Made you think about how you might be doing certain things that you could do in the early years, you could do with reception class, you could do with 6-year-olds, 7-year-olds. And also problems that you might tackle with much older children, 16, 17-year-olds. And now that football game is one I really like because there are over 200 solutions there. And what I would do with that would be to put a big sheet of blank paper on the wall. I would have give them some clues so that they could get a few solutions, and then I would start to think about how you might organize the solutions. And I'll give you a little bit of insider information here that I think you could arrive at for yourself if you did some thinking about it. The zeros the O's in foot are not 0, but they can be 0 and they can be 9 and they can't be anything else. And if you look on the Aiming High website, you'll find a complete explanation of how you work out a system for finding the answers. A system is a way of putting them in a certain order so you can check that you got everything and you haven't missed anything out. The other brilliant thing about having a problem that has got lots of solutions is that the whole class is working as a team to find solutions. As soon as anybody gets another solution, they come and add it to the chart on the wall. And it can go over 2 or 3 weeks or even longer. Football, anyway, as a game, is so popular. This one appeals to children. Not that you need to spend a long time on it, but if you can persuade the children to keep coming in with answers, if they think about it, you give them just homework to work on it a bit more. For the older children, they can do some computer programming and write a program to find all the solutions. And a lot more information about it is available on the Aiming High website. Right, so here we have the links that I told you about. All of these problems that we've been looking at today. It's a lot more information and solutions and a lot of some suggestions for teaching on all of these examples. So all our resources are freely downloadable. There's worksheets for everything. There's inclusion and home learning guides with activities for all ages and attainment levels. There's solutions, there's key questions, and there's diagnostic quizzes for formative assessment. Also, you can find on the YouTube channel previous G10 workshops. They're recorded there. Have a look. Every day we publish a new challenge on the AIMSEC Facebook page. Have a look at our Facebook page and you'll see there's lots of interesting ideas there for teaching to enrich your lessons, make them more enjoyable. It's time to say goodbye. So it's goodbye from me. And
From me.
we want to thank you for coming to the workshop. Please use AIMSEC ideas on the Aiming High website and add comments there. Share what you've learned with other teachers.
Bye, Janita. Bye, Alfred.
Bye-bye. Thank you so much. Brilliantly
Thank you.
done.
Bye.
Thank you. Bye-bye.
Bye. Bye.
Bye. Bye, everybody.
This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.